talk about this abstract formulation for statistical solutions. So I've been talking about statistical solutions for a while already, like 10 years, I guess. But this is something that started maybe 4 years ago, and I think only now we are getting some results. So this is a joint work with Anne Bronzi and Cecilia Mondaini. Anne was a student of Helena and Milton in Campinas, and she's doing a postdoc here. She's sitting here, postdoc with me, and Cecilia is a doctoral student at the Federal University, my student. So it's been very good to work with her, with them. We have been meeting twice a week, and it's very, very lively. And this is a tough subject that we address more functional analysis than PDEs. And so I had to learn a lot of stuff and measure theory in Hausdorff space, so we don't have a metric space and things. So I've been learning a lot with them and in this group. So let me say a few words about statistical solutions. So the aim is to describe the evolution of probability distributions of initial conditions. So we have let's say an evolution equation, and we are used to looking at one solution and see if, given an initial condition, we have a solution or not, and how that solution behaves. And this is to look at a collection of initial conditions, maybe give probability for each of them, and see how the distribution evolves. And so they are related to the transport of measures by a semigroup. But the statistical solutions, the fun thing is that is the case when you don't have a semigroup. So what we do when we don't have a semigroup. And this concept has been introduced for the study of turbulence in Navier-Stokes equations by Foyaz and Prodi. And our aim, what we are trying to do is to extend these things to an abstract context that applies to other equations. So just a nice picture here. So let's say that we have a simple ODE. With this solution, we have 3 stationary solutions, and the other solutions converging to 2 of them mostly, and then 1 unstable solution here. So that's usually what we look in ODE, studying ODE or PDE. But then we can consider a collection of initial conditions, give some probability distribution for them, and see how they evolve. So they will mostly accumulate on these 2 solutions here, and this will be the probability distribution after some time. So we can do this for ODEs, and this is what people do. Let's say in ergodic theory, they look at invariant measures, which are, let's say, stationary solutions for this kind of problem. And we can do this for PDEs too, when you have a well-defined semigroup. And what we want to do is, when we don't have a semigroup, what can we still talk about the statistics of the flow. So the motivation for studying this in general is when you have some uncertainty on the initial condition, or when you have some sensitivity to the initial, especially connected to the sensitivity to the initial condition. So we don't know exactly the initial condition. So we maybe look at a collection of them and see how they evolve and get some probabilities of the situation later. And one practical example is in weather prediction. If we go to the site homepage of CPTEC, the Weather Prediction Center in Brazil, and you look at their homepage, and there you select models, and they have several models, and 2 of them are ensemble regional and ensemble global methods. And what they do is exactly this. They assume they consider one method, the ETA method that they consider, but they assume that they don't have so much certainty on the initial condition. So they take one initial condition and juggle around and take initial conditions close to that, give some probabilities to them, evolve each of them, and look at the end the situation that we have, the state that we have after some time, and connect that with the probabilities that we started with, and you have the probabilities of the prediction. And I was going to say something, I forgot. So this is a major issue in climate because the data that you get from the atmosphere is very spread out, very isolated. So there are several ways to interpolate the data and get an initial condition. So you have a big uncertainty on that. And besides, it's a very sensitive problem. So it's important to do that. So just to illustrate the object that we are studying here. So again, if we have a semigroup, if we have a differential equation in a semigroup, S of t, then this is just the transport of the initial measure by the semigroup. So the probability, mu t, the probability that at some time t, is just the transport of the probability at the initial time. So how do you read this? If you want to see the probability of some set E, then that's the probability, the initial probability of the pre-image of this set. So that's a picture for that. So at time t, I want to see the probability of this set here. Then I take the pre-image and look at the probability of this set from the initial measure. So another thing that you can see is that if you have an initial measure with a certain support, it will evolve to another support, and then you can look at asymptotics of that and invariant measures and things like this. But at this time, you're just looking at the finite time evolution. What we are looking at this point is like an initial value problem. Given an initial measure, how we obtain this family of measures, given the probability at the future time. So that's what I just said is when you have a semigroup. And then that's just the transport of the probability distribution. And the aim of the statistical solution, the notion of statistical solutions, is to adapt this to the study to the case where we don't have a semigroup, when you have an equation which is not well posed. Well, we don't know that it's well posed or not. And the main motivation is the 3D Navier-Stokes equation that came from that. So in turbulence theory, this is to make rigorous the notion of ensemble average. One thing that we look in turbulence theory is this average. You see, you have several solutions, probabilities associated with this solution, and then when we want to see some mean field, mean velocity field, or mean pressure, or whatever, you take an average of the pressure along, and that's the ensemble average. And the statistical solutions is the probability associated with this ensemble average to make this notion rigorous. So in a sense, I like to say that the theory of statistical solutions is to ensemble averages, as the theory of weak solutions is to individual solutions. So we can look at an engineer can look at an equation, evolution equation, assume that we have a solution, don't care about the regularity of that solution, and deduce things. But we look at weak solutions at the minimal regularity that we have, now results that we can prove existence. And that's how the weak solutions are to the individual solutions. And the statistical solution is the same thing, but related to the ensemble average that are used in turbulence theory. So as I said in the beginning, our aim is to extend the current results done for the Navier-Stokes equations to extend to other systems. The main results for the Navier-Stokes equations were given first by Foyaz and Prodi in the early 70s, and Vishik and Fursikov in the late 70s. And by this, I mean main results in terms of the initial value problem, given an initial probability to find the distribution at the future time. Of course, you can do other things like analyze the regularity and other physical quantities associated with turbulent flows. So there are several results on that, but I'm speaking here just about the initial value problem. And more recently, we have formulated a notion that it's actually a kind of combination of these two, or an improvement on this one here. But the main ideas are in these two here. We just reformulate them slightly. And now, more recently, for the abstract formulation, this started in the Master of Science dissertation of Cecilia in 2010. that's when he defended her thesis. The project started in 2008. And, well, usually for a Master of Science student, you give her a paper that's been published already and let them read and understand. And this time it was a bit of a challenge because I decided to give her a problem that I didn't even know how to go about. So it was, so I had to work a bit, and she had to work a lot, but we managed to obtain some nice results. And then more recently, then she started her PhD, and then Bronze came, and we made a group there, and so they studied Navier-Stokes equation and statistical solutions, and then last year we started more seriously about this abstract formulation, and now we are getting some results that I wanted to describe here, not in detail, but just give an idea what we have been doing. So the two notions that I mentioned about statistical solutions, Fayas-Prodi and Vyshik-Fursikov, are of the following form. So let's say that we have X is the phase space of the equation. So we have some PDE that is in L2, the solutions are in L2 or in H1, and the Navier-Stokes equation is essentially L2 with divergence-free condition and the boundary conditions. So, but in general, X can be any phase space of your PDE. And then the statistical solutions are a family of probabilities on this space, where at each time t you have a probability of the distribution of the state of the system in the phase space. So we have at the time here, the space X, and this is just an illustration of the support of the measure mu of t, say. And how this measure relates to the Navier-Stokes equations is essentially through an equation like this. And this equation is a kind of weak formulation, but not exactly in the sense that we are more used to in PDE, but it's a kind of weak formulation that we have a function phi, which is like a test function, but it's not a function in the physical space of the equation. It's a function on the phase space. So, and this represents some moment. Let's say I take the average of the velocity field at some point or in the whole space. So phi is a function on the phase space. And then there's the probability associated to this quantity. And this is how this probability evolves with time. It evolves according to this equation. Essentially, it's a chain rule. I look at phi of u of t, and I take the derivative of that, and the derivative of phi of u of t is u prime, which is f of u, and phi prime. So it's like a chain rule, but average in the space, in the phase space. So that's the notion developed by Fayas and Prodi. And in the same decade, some years later, Vyshik and Fursikov came with another formulation, which is of a probability measure, not in the phase space X, but on the trajectory space. So this X here, this wiggled X or calligraphic X, is essentially, well, not, it could be some LP function with values in X or some space of continuous functions with values in X. It is a space of trajectories. And rho is a measure on this space of trajectories. So here's an illustration of that. So you have the X and T. So all the functions here are the phase space. And you have some measure supported on this, defined on this space. And it's carried, so the measure, it's a probability measure, and it's carried on this space U where you use the set of all weak solutions. So the way to relate the measures, the statistical solutions, to the Navier-Stokes equations are through the carrier. So this is quite natural too. From one sense, this is more natural. You can look at each time the probability distribution, but this one is also a natural way to see this object. So this have been done for the Navier-Stokes equations. specifically for this equation. And in this case, the functional setting for the space, well, I'm talking about the function spaces to tell you what the space X is in the general case. So the usual function space for the Navier-Stokes equations, the classical one, is the space H, which is the L2 vector field with divergence free, and in the boundary conditions could be periodic or no slip. And the space V, which is the subset of this one with the H1 vector fields. And other important space are the dual of V, when you identify H with its dual. Domains of the Stokes operator, the linear part of the equation. And a particular space that is useful for us is the HW, which is the space H, but endowed with the weak topology. This will be a fundamental space for us here. And then, in the functional approach, I mentioned a phase space and a trajectory space. And for Foyas and Prodi, the first work on this, they consider the phase space as the space H, and the trajectory space as L1 of 0Th. But for Foyas and for Vishing and Fusikov, they don't project, so they don't use the phase space. They don't care for the phase space. And the trajectory space is this one here. These are all natural space. This is the natural space for the solutions of the Navier-Stokes equations. Okay. And it's continuous if we take this space here for S bigger than 2, and you get this continuity here. And more recently, we modified things a little bit to consider the space HW as the phase space, and the trajectory spaces are the space of continuous function with values in HW. Okay. This has some advantages. And the existence of statistical solutions, the first two used essentially Galerkin approximations, and what we did was some conversions of a convex combination of direct measures. I might say a little more words about this later. And for the projections, if you want to get a statistical solution in the sense of Foyas-Prodi, you're going to project in the phase space, and then Foyas and Prodi, they use Foyas actually use a complicated representation of the dual of this function here. We have a measure. Well, we look at moments here, and so we are concerned with the dual of this space here, and then so when we want to project the operator at each time t, since this is not continuous, this is a certain this is problematic, but you can use some complicated representation of the dual to solve this. Vishing and Fusikov do not project, and for us it's very easy since we use this space here. Just by using this space, the projection is very easy because the operator that takes a function in the trajectory space to its state at time t is a continuous function. So we can just project a measure without any problem. And that's the main advantage of this. This is the definition of statistical solution in the sense of Foyas-Prodi. I'm not going to go into the details of that. There's an issue here at time t equals 0, which will be important for us later. But I'm going to mention this a little later. So for Vishik and Fusikov, as I said before, they use a trajectory space which is this one here. So the individual solutions are here, and the statistical solutions for them are a measure, a rho carried by a Borel subset W made of weak solutions, but not necessarily of Rayleigh-Hopf type, but it's of weak solutions. And another important fact, here is this energy inequality in the mean. Here is a mean form of energy inequality. But it's not a very sharp one. So if you compare with the definition Vyshik-Fursikov, you got this energy inequality, which is quite similar to the energy equality that we have for individual solutions. This is just an average version of that. And the energy estimate used by Vyshik is not the energy inequality that we are used to. It's just a control of the L2 norm in space and the V norm here from the initial condition, but it's not very sharp. You add one here and you don't have much control of that, but just some kind of boundedness, an a priori estimate to help things work. And that's related to the fact that they are not using Leahy-Hopf inequalities. Okay. And for us, more recently, so we consider this trajectory space, and we consider the weak solutions on zero infinity. Leahy-Hopf weak solution, I should have written here. So we consider Leahy-Hopf weak solutions, and this is the trajectory space, and the statistical solutions for us are essentially measures rho carried by U. That's how it should be, but it's not quite like we did. So we start with a measure rho carried by the closure of this set here, and then ask it for some like this, just to say that it's the kinetic energy is finite in the mean, in average, and this is the continuity at time 0. So the main issue here, the two difficulties here is that the space of weak solutions are not closed. Let's say if I take a bounded set of weak solutions, it's not closed. And the reason is that the weak solution, the way most people define it, the way we consider, not everybody do that, but the way we consider is that they are weakly continuous in time with values in age in the weak topology, but they are strongly continuous at the initial time. And this strong continuity at the initial time is important to get a priori estimates from the initial condition. If you don't assume that they are strongly continuous at their initial time, you may not get that they are bounded. So you take an initial condition, you may find solutions that are not strongly continuous at the origin, and that they are not bounded. So the strong continuity at the origin is important, but then when you take the closure of some bounded set there, you may lose the weak continuity at time 0. And that's bad when you take like measures and limits of measures, because you may, even if you start like with measures that are carried here, and you take the limit in some sense, you may leave this space and get into the closure. So that's the difference between U and the closure, is the strong continuity at time 0. And if we ask for some continuity in average at time 0, then you can recover the continuity everywhere, or almost everywhere at least. So actually what we have is that that rho is actually carried by U. So the rho defined as before, which is carried by the closure and strongly continuous in average at initial time, we may actually deduce that it's carried by U. So we could have started as this is the definition and have more work to prove the existence, but that's not how we did. So that can be seen as a regularity result. Okay. So my time is running out, so I think I will just skip to the abstract definition. So our aim was to try to come with a framework that could apply to other equations. So at first we were worried about equations related to the Navier-Stokes equation. So let's say coupled with the temperature, or coupled with salinity, or some magnetic field, to avoid going through all the work again, because if you look at the proof, it's a very long proof, full of details, and we wanted to see if we could get things, well, clean things up and see what's really important in the proof, and see if we could get framework that would apply to all these problems. And we had some hope to see, well, when we started to work on this, at some point, I think we were happy to realize that the hardest thing is to prove the existence of individual solutions. So for that, you have to be careful on each equation, in each equation, how to prove the existence for each equation. But once we have that, then you can put them in a framework that's good for all of them. So you can be more hopeful that things will work. So the first ideas were to look at the Bénard problem and MHD and quasi-geostrophic equations. But we haven't done that yet, but we hope to be able to apply to other equations too. And essentially, we start with the topological Hausdorff space, just that, and the initial probability distribution, and we assume that it's tight. So in the application, in the Navier-Stokes equations, we usually assume that the measure has finite mean kinetic energy. And here, there's no kinetic energy. We're in an abstract setting, and we came up with this definition that was natural from the point of view of the probability theory on Hausdorff spaces, and actually natural for the applications. So that fit nicely. And then we assume that there's a set of solutions U, some set, abstract set U as a subset of the trajectories, which has this essentially three properties. One is the projection at time 0 of U is the whole X. This essentially says that the global existence of solutions. For each initial condition, I have a global solution. Essentially, that's it for this assumption. This one here is some kind of a priori estimates. So if I start with, I forgot to write here, if K is any compact subset of the space X, then this space is relatively compact in the calligraphic X. So it is essentially some a priori estimates in practice. So it was also very natural. And why is this important? Because we are in a topological Hausdorff space. Do measure theory here is complicated. But if you are in a compact subset of this space, then you got a normal space, and things work out fine. We don't have many problems here. And for in some situations, I envision that this set might be compact already, and then we are done. But for the Navier-Stokes equations and related equations, there is that issue with the initial time. And for that, we need some characterization of this set within this set. And then we can do this characterization in terms of a lower semi-continuous function V, which in the case of the Navier-Stokes equations is essentially the L2 norm, the square of the L2 norm. And in other equations, there might be something related to that. If I couple that with the temperature or salinity, then we'll have exactly the same thing. So we need some characterization of this set, and then we can obtain a trajectory statistical solutions in this sense. There's a Borel probability measure rho, which is tight in X, and it's carried by a Borel subset in U. Because we don't assume that U is Borel, we don't know that. But if you but you can prove that there's a Borel set V inside U where rho is carried. And then we can prove that this result, that given a tight Borel probability measure μ0 on X, there exists a measure rho, which is the U trajectory statistical solutions, with this initial condition. So we are still working on all the possible applications, but I think we got a nice result of this work. I'll stop here. Thank you.